Hi everyone! In today's video we are going to be looking specifically at polynomials that are called cubic functions. We are going to evaluate and also spend a fair amount of time graphing them today. Today we're going to focus on graphing the parent function for cubic, and then we're going to use that cubic parent to we're going to transform it, and that's going to give us the whole family of cubic functions. We are also going to be talking about turning points today, because turning points are going to be really helpful in graphing polynomials that are of higher degree than a cubic or a third degree polynomial. So we're going to look at figuring out how many turning points a polynomial equation has just by looking at the equation. Okay, so first let's look at the parent function for a cubic. Notice here in the equation that you have an x that's raised to a third power. So let's go ahead and plot some points and graph them to see what shape the cubic's in first. Okay, so let's do some evaluating. Let's plug in -2. So we're looking at what is y equal to when -2 is raised to the third power. -2 cubed is -8. So that's a -8 there. When we plug in a -1 to see what the y value is, we get -1. When we plug in 0, 0 cubed is 0. When we plug in a 1, we get 1, and when we plug in a 2, we get 2 cubed is 8. Okay, now do you notice anything about those numbers? Do you see some similarities? On the left-hand side, the negative side, the y values are also negative. On the positive side, they're also positive, and you see that pattern, that 8 and 8, the value, the absolute value is equivalent. Okay, so let's graph these and see what's happening with that similarity. So I'm going to start with my -2, -8, which is going to be down here. Then I've got -1, -1, 0, 0, 1, 1, and 2, 8. Okay, so let's look at what's happening here. That is our parent function for a cubic, x to the third. Now, I want you to notice that in the center of this point 0, 0, we're going to call that, for our purposes right now, the initial point. Because if you look at that initial point, there is some form of symmetry that's happening around it, where you have this side that goes over 1, and then up 1 cubed, which is 1, then back from the initial point over 2, up 2 cubed, which is 8. And on the left-hand side, when we go to the left one, -1 cubed is -1, and -1, 2 cubed, that is -8. So we're going down 8. That nice pattern is going to help us when we're graphing these other transformed functions. We're going to start with the initial point, and then we're going to follow that pattern of going over 1 unit, cubing 1, and going up that far. Going back to the initial point, going over 2 units, cubing 2, and going up that far, unless there's some dilation, which we'll get into in a few minutes. Okay, so let's just talk about some basic transformations first, based on this initial point. Okay, so let's first just sketch our cubic equation. I'm going to use red for the parent function here. My initial point is 0, 0. We just determined that. So now I'm going to go over 1 unit, and then 1 cubed is 1. So I'm going to go up 1. I'm going to go over 2 units. 2 cubed is 8. So I'm going to go up 8. I'm going to go to the left and do the same thing. -1, or to the left 1, cubed is -1, so I'm going down 1. When I go 2 units to the left, that's -2. So -2 cubed is down at -8, and that gives me my parent function. Okay, so look at this next one, x to the third plus 2. Now, this k value is going to be the same kind of k value that we've been looking at all year long. It's going to determine a vertical shift. So our initial point is going to move up 2 units. That means the new initial point, and let me change my color really quickly, is going to be at 0, 2, because it moved the y value up vertically 2. So my initial point is now at 0, 2, which means then that when I draw the rest of this graph, when I go over 1, 1 cubed is 1, so I'm going to go up to there. When I go over 2, I'm going to go up 8, which is going to be up here. When I go to the left, that's going to take me to that point, and then 2 to the left, down -8 is going to take me here. So that means then that that blue guy is shifted up 2 units. What do you suppose this k value of -5 is going to do? Are you thinking that it's going to shift it down because it's a vertical shift? If you are, that's right. We're going to take our initial point and we're going to go from 0, 0 and move it down 5. So that puts our initial point here at 0, 5, and then let's follow that pattern. When we go over 1 unit, 1 cubed is 1, so we're going up 1. Go back to the initial point. When we go over 2 units, 2 cubed is 8, so we're going up 1, 2, 3, 4, 5, 6, 7, 8. We are going to follow the same sort of pattern down the other side, which moves our graph in green like that. So again, notice from the red, the blue, and the green both moved up or down depending on which kind of shift the k value is having. Okay, so I'm going to go back to red again, and let's look at the h value, the horizontal shifts. My initial point for the parent is 0, 0, so I'm really quickly going to plot that parent so we can watch how he moves around. Okay, so that's my parent. And for this next one, do you see that the h value is inside of the quantity that's being cubed? That h value is going to behave in the same way that our horizontal shifts have happened before. So if it's a positive sign, we're going to move to the left. That's -3. And the y value is not going to change because k hasn't changed. So that means we're moving to the left 1, 2, 3 units for our initial point. And then we're going to follow that pattern of going over a value and then cubing that number to figure out how far to go up. So it's going to give us this graph. Okay, let's do one more. Do you see the h value in this last one here? Which way do you think that -2 is going to move it? Is it going to move it to the left or to the right? It moves it the opposite direction, so if it's a -2, it's not going to move it in the negative direction, it's going to move it in the positive direction. So that takes us over to 2, 0, and then we can follow the same pattern of cubing as the parent that we've been doing to get the rest of those y values. Okay, so there are my horizontal shifts. Notice that the initial point that started at 0, 0, depending on what h was, either moved it left if it was a positive number or right if it was a negative number. All right, last thing we need to talk about is the a value. That's the value that's out in front of the quantity that's being cubed. That a value, just like before, is going to give us a dilation, meaning that it's going to either vertically stretch or shrink the parent function. So my initial point for the parent function is 0, 0. Let's graph him again real quick. Okay, and now let's look at some dilation problems. This first one, the a value is 2. That means it's going to double the y values when I plug in an x. So if I am starting from the same place, because h and k haven't changed at all, I'm starting at 0, 0. That's still here. But now, when I go over 1 unit, instead of going up 1 cubed, which is 1, I'm going to go over 1 cubed times 2. So 1 cubed is 1, but then times 2 is 2. So that's going to take that value up there. Going back to my initial point, when I go over 2 units, 2 cubed is 8, but I have to double it. because of this 2. So I'm going up not just 8, but 16. That's way up here somewhere. When I go in the other direction, over 1 unit, negative 1 cubed is negative 1, but then I double it, so that's negative 2. Going back to my initial point, when I go over 2 units to the left, negative 2 cubed is negative 8, but I have to double it. Negative 8 doubled goes all the way down to negative 16. So this one, look at how much thinner or more narrow he got. That got stretched or pulled more in and up, vertically pulled or stretched. Okay, let's look at this next one. The A value is 1/2, which means this time we're going to be cutting the Y values in half as we graph them. There's no H and no K, so I'm still starting with my initial point of 0, 0. But this time I'm going to go up and down less as I draw my Y values. So when I go over 1 unit, 1 cubed is 1, but I only go up half of that, so I'm only going to go up a half. When I go over 2 units, 2 cubed is 8, but I'm only going to go up half of that. Half of 8 is 4. If I go to the left, I go over 1 unit, 1 cubed is 1, or negative 1 cubed is negative 1, but I'm only going to go down half of that, so I'm going down negative 1/2. Going back to my initial point, going over 2 units to the left, that's negative 2 cubed is negative 8, but I'm not going to go all the way down. I'm only going to go down half of that, so I'm going to go down 1, 2, 3, 4. Okay, so let's see what that looks like now. There he is. Notice that he is a little bit wider than the red parent function that we just drew. That means he is shrinking vertically. He's getting squished down. Kind of looks like the silhouette of someone sitting in a chair. He's sitting a little bit more deeply or squatting slightly more deeply than the parent function was. All right, we have one more to look at. What's happening with that A value? Negative x to the third. Do you see that you have this negative A? Let's look at what that's going to do on an actual table. Okay, so my initial point is still 0, 0 because I have no H and no K values changing the parent function. So I'm still going to start at 0, 0. But when we look at some points nearby, let's look at 1 and 2, negative 1 and negative 2. If we plug in 1 to that, so that's negative 1 cubed. 1 cubed is 1, so that's negative 1. That puts our point at 1, negative 1 down here. When we evaluate at 2, that's negative 2 cubed. 2 cubed is 8, so that's negative 8. At 2, it's down at negative 8. At negative 1, negative 1 cubed, negative 1 cubed is negative 1. So 1 times negative 1 is positive 1. Oh, look at what's happening. When we evaluate at negative 2, negative 2 cubed is negative 8. So negative 8 is positive 8. What has the A value done then? Do you see how it has flipped it? So that the part that was a positive Y value is now a negative Y value, and the part that was a negative Y value is now positive. It flipped the whole thing across the x-axis. So the A value does two things. Besides the stretching and shrinking that happens, it can flip it if the A value is negative. Just like a parabola would flip over and open up down instead. Okay, so let's summarize. Here is the general form for a cubic. When A is positive, the graph is going to look like most of those graphs looked like. It's going to be an increasing line with a little squiggle in the center that has an behavior of negative infinity going up to positive infinity on the right. When A is a negative number, the graph is going to do that flipping thing that we just looked at. So it's going to be a decreasing line instead of increasing, and it's going to go on the left up to positive infinity and on the right down to negative infinity. When do you have a graph that has a vertical stretch? What changes there? Remember, stretches and shrinking all have to do with the a, and it has to be an a value that is greater than what? 1. The absolute value of a has to be greater than 1. The shrinking is going to happen when the a value is between 0 and 1. So it's going to be, in other words, a fraction, a proper fraction. Okay, the h causes a shift on which axis? Remember that h is the horizontal movement, and the axis that is going horizontally is the x-axis. The k causes a shift that's happening vertically, which means that it's a shift on the y-axis. And the initial point is hk, those two values from our parent function, the one that's inside the quantity that's being cubed and the one that's outside being either added or subtracted on. Okay, so the last thing that we need to talk about is just a quick little bit of vocabulary. We've talked in previous chapters about mins and maxes, relative mins and relative maxes. So when a polynomial function has a turning point, one of these places where you have a relative min or max because it turns to go the other direction, you're sometimes going to see the word local instead of relative. These mean the same thing. A local max is the same thing as a relative max. A local min is the same thing as a relative min. So the reason that this vocabulary matters is because there are a couple of facts about turning points in polynomials. The first fact is that the graph of every polynomial function of degree n has at most n minus 1 turning points. So think about that for a second. Let me just give you just kind of a random polynomial here. Let's imagine this guy for a second. Thinking about this, a graph of a polynomial function of degree n. So what is the degree of this polynomial that I just made up? The degree is the largest exponent, which means that the degree is 5. So if n is equal to 5, it has at most n minus 1 turning points. So what if we take our n and subtract 1? N minus 1 means 5 minus 1. So that means just by looking at this equation and doing this quick little bit of math on the side, I know that at most this equation, when you graph it, is going to have 4 turning points. If a polynomial function has n distinct real zeros, then the graph has exactly n minus 1 turning points. So let's think about that for a second. Imagine you have been given a polynomial that has 3 real zeros, meaning it crosses the x-axis, the x-axis at 1, 2, 3 spots, here, here, and here, let's say. So that means then, or this fact means that the graph has exactly n minus 1 turning points. So if the n is the number of zeros that it has, that's 3, the turning points are equal to 3 minus 1, or 2. And if you look at this quick sketch that I just drew, there's a turning point here, and there's a turning point here. So that is 1, 2 turning points. Okay, so there are a couple of problems for you to work on in the Now You Try. You are going to be doing some graphing using the parent function for cubics, which we just did some work with, transforming it all over the place to get other cubic functions from the family. And there are also some questions about the turning points and figuring out some quantities if you know either the turning points, the degree, or the number of zeros. So go ahead and give those a try.